structures. So now let us come to resonance effect. Fine. Yeah. So here we are, resonance effect. How do you consider that resonance effect? Yeah, good Sankalpa, you joined. Last time we had completed this part, or this was remaining. Do you remember this? Different resonating structures. Wi-Fi issues. Okay, fine. Okay, okay. I think yes, we had done this part. We were now supposed to be moving to, why I wanted was that whether we had talked about different resonating structure, that how the double bond shifts between the different carbon atoms, that is, it is called as delocalization. We have different canonical structures. The screen is seen and I'm audible. Is that fine? No, I hadn't shared, Sankalpa. That was the reason why you were not able to see my screen. I did not do the screen sharing part, which I did just now. I think now that's what I want to ask you. Is my screen seen here? Is it seen? Okay, fine. Good. So let us start with resonance effect. Now here, what is the resonance? We talked about inductive effect, resonance effect we were discussing. In that, the other day you asked me about pi bond. So that pi bond last time I explained. Now going to the different part of this is what is actually resonant effect. So here let us talk about the existence of resonance often results in developing polarity in a molecule. So when a molecule is neutral and then it would be inducing polarity. Polarity means you have a positive and a negative, that is poles are formed, that is partial positive, partial negative charge. The polarity produced in the molecule by interaction between conjugated pi bonds, or that, now you know what is conjugated pi bond, or that between pi bond and p orbital on attached carbon atom, or any charge which is there, is called as resonance effect or mesomeric effect. Okay. Conjugation is alternate double bond and a single bond. The effect is transmitted through a chain of conjugated pi bonds. So here the effect is transmitted through that different chain. There are two types of resonating effects. Now here also, if you remember inductive effect, do you remember inductive effect? We had done inductive effect wherein it is a permanent effect. And it is, say for example, it is chloroethane, yeah, bromobutane. Then the inductive effect is felt on the first carbon atoms, or nitroethane, nitromethane, which is a permanent effect. We had discussed that. And now coming to here, the effect is transmitted through the chain of conjugated pi bonds. There are two types of resonance effect. Now let us, they are again plus R, just like plus I and minus I, you have plus R or plus M, and negative effect, that is minus R or M minus M. Now positive resonance effect or electron donating or releasing resonance effect, same thing, that is here, and negative will be the one which is going to pull the electron towards itself. If the substituent group has lone pair of electrons to donate to the attached pi bond or conjugated system of pi bonds, the effect is called as plus R effect. Just understand it. I know that it will be a little difficult to understand, but when I show this, then it will be easy for you. I'll show it on the whiteboard. First, let us read it. Now, which are the groups which are going to show us that plus R effect? Groups such as OH, OR, O- negative, NHR, halogens, etc. Because they have this lone pair of electron, and this lone pair of electron can come in conjugation with the ring. That is, it can come here with the ring and it can be delocalized over the ring. That is the resonance effect, and you have so many different structures which are known as canonical structures, and each structure is represented by a double-headed arrow. जैसे अनेक structures benzene चे जितकी जास्त resonating structures तितकं जास्त molecule is going to be stable. They have lone pair of electron. This plus R effect increases the electron density at certain positions in a molecule. Now, at which positions in a molecule the electron density is increased, that will be seen. Now, let us see this example. Before that, let me know that do you remember what is ortho, meta, and para? Can you just tell me? आठवतंय का तुम्हाला what is ortho? Sorry. Where am I? So I want to see. Do you remember what is ortho, meta, para? In the benzene ring, I had explained you, or you don't remember. And just say, for example, Acha, in this ring, can you tell me what happened? Which is ortho, meta, para? Let me number this. Yeah. In this case, which is ortho, meta, para? Do you remember at least there is ortho, meta, para, or no? Again, I need to teach you? Okay, ortho is 1, 2. Fine. Only 1, 2. This is the benzene ring. When it is like this, there is nothing as ortho, meta, para. All the positions are equal. Okay. Now, you can talk about ortho, meta, para only when it is substituted like this. Then only you can talk about this is. In this case, now 1, 2, I'm considering this as 1, 3, 4, 5, and 6. Then you have these two positions, that is 1 and 2, and 1 and 6 are ortho position. Then you have 1 and 3 and 1 and 5, they are meta positions. And you have 1 and 4 as the para position. Okay. Do you remember this? Have you understood this? You cannot say anything when there is no substituent. That is, there is no substituent in this ring. Then you cannot say anything as ortho, meta, para. Do you agree to this at least? When या कळतंय का? ज्या वेळेला नुसतंच असेल ह्याच्यामध्ये सबस्टिट्युएंट नाहीये तेव्हा मी विचारू शकले तरी तुम्ही मला सांग वेन यू हॅव विथ रिस्पेक्ट टू व्हॉट दॅट शुड बी अ क्वेश्चन ऑल द पोझिशन्स आर इक्वल नाउ सपोजिंग इफ आय हॅव अ सबस्टिट्युएंट ॲट दिस पोझिशन ओके then my position this becomes 1. It can be 2, 3, 4 or 1, 2, 3, 4 clockwise, anti-clockwise, whatever you want to put in, but need not be that always this is 1. Understand that. It can be 1, it can be here also. Say for example, I have this as x. Then now my ortho position, they become as this is going to be my ortho position, this is going to be my ortho position. Then this is going to be my para position, and these two positions are going to be my meta position. Are you following it? Sankalpa is only telling me yes. What about you, Sameer? Okay. Why I want to tell you is because here now I'm going to talk about, that is now the resonating effect. Now what is the resonating effect we are going to show over here is that, let us have a look at this. This is NH2. Okay. Now this NH2 has got a lone pair of electron. So this is going to show that plus I effect. So how will you show that? Now this electron pair is going to come into the ring. This is the delocalization. So now you can see that this electron pair is coming into the ring, and you have these various different resonating structures which make this structure as stable. So you can see that the electrons, they form a double bond over here. Okay, so this gets plus charge. Why? Because you can see that valency of nitrogen now over here is 4, and this electron pair comes over here. So here you are. Are you following what have I done? Is it clear to you? Just have a look at it. Are you following what I did over there? I'm trying to bring the electron pair of on nitrogen atom into the ring for delocalization. Why? Because this is going to give me different resonating structures. Okay, so let us go back to the, yeah. Now, next step would be, I'm purposely taking different colors. You can see that over here and then over here. So here, this bond which is already over there, it remains just like this. Positive charges over there. So these are different resonating structures. Now next step again would be these electrons, they would be coming over here, and these electrons would be going over. See, the charge is moving alternate. Here you have one plus charge, then a double bond, then you have the negative charge, then single bond, then double bond, single bond, double bond, single bond, double bond, charge. Same thing you can say, you cannot have the charge and double bond on the same carbon atom. So now you can have it over here is, so here you are. So you are getting this as the structure. So these are various structure wherein the effect is plus R effect. Okay, yeah, plus M effect. Is it clear? Have you understood what am I done or what I am doing over there? कळतंय का? नाही कळत असेल तर पुन्हा एकदा. Okay, fine, good. So now here you are. see the plus R effect increases electron density at certain positions. So now if you see where has the electron density increased in this case, plus R effect which we were just now doing, because of that you can see that the electron density has increased over. Now can you tell me where do you see the negative charge? On which positions can you see the negative charge? It is clear on positions ortho and para. Am I right? So this is ortho, and this is para. You are getting, see the negative charges over here at ortho position. The negative charges over had, not the charge, I mean the electron pair. And here also you can see the electron pair. So it has increased the electron density. But whereas this meta, it does not come into picture. You can see that the negative charge moves over the ring but at ortho and para position. Once again, I'll just try to show you that what I have done in this case. What I have done was, you can see that this is amine. In this amine, you have nitrogen aniline, which is called as, it has got lone pair of electron. This lone pair of electron can be used to delocalize over the ring. So here you can see why I'm putting plus charge, because I have used the electrons over here, and nitrogen, the valency, look at the valency of nitrogen, it is 4. And then the electron pair is coming over here. It has traveled from here to here. Okay. Similarly, now for this to travel, it will be over here, and this will go over here as electron pair. It won't go as a bond, because if it tries to go as a bond, one of the carbon will be unstable because of the valency, which is more than 4. Then next it will move over here, and from here it will move over here. So this shows that the electron density is at only ortho and para position, but not at meta position. These are various resonating structures. Okay. So you can see over here, they have also shown it into the book that here you have oxygen, ortho position, meta position, para position. This is the lone pair of electron on nitrogen atom, which is coming into the ring. And these are various delocalized, it is delocalized over the ring. These are various resonating structures. So this is nothing but plus R effect of ring. Now, just as it has plus R effect, now what happens, it also has negative resonance effect or electron withdrawing, that is called as minus R effect. Now, have you understood so far that how I have shown the effect? What is it? Where there is no bond. I haven't understood. What do you mean by where there is no bond? What was this answer to what? Where there is no bond?
Ma'am, I was talking about the charge.
Okay, it's not a question, no? You have understood what?
Yes, ma'am.
Okay, fine.
It was not a question.
It was not the question. Okay, okay. Fine. Now come to the next part. We will go now the exactly opposite effect. Now here in this case, have you understood where is the electron density more? Can you tell me? Just put it into the chat box where it is the electron density more on which positions when it is plus R effect. Yeah, when there is plus R effect, you have electron density more at which positions? It is more on ortho and para position, the electron density. Yes, ortho and para. You saw na and on that when I was showing it, where was the charge over here? It was like this, right? इथे होता ना? Here, here. The negative charge was over here. And this was plus. Similarly, you had different form. Yeah, and the third one was this. NH2 plus. Okay. So these are various structures. Now coming to exactly opposite effect. That is here now the electron will be pulled. See the fun how it what happens over there. Now let us just read this. If the substituent group has a tendency to withdraw the electrons from the attached pi bond or conjugated system of pi bond towards itself, this effect is called as minus R effect. So which are the groups which will show that is now instead of coming towards the ring, it will go away from the ring. So groups such as COH, CHO, CO, CN, NO2, they show minus R effect. Okay, the minus R effect results in developing a positive polarity at certain positions in a molecule. So let us see what happens. So here you have, they have taken one example, that is the nitrobenzene example. So for nitrobenzene example, this was an amine that is now a nitro group which is introduced into the benzene ring. So when you have say something like this, this is how you put in your nitrobenzene. That day I had shown you. Here you have. Okay, and here is the ring. Actually, it is nothing but it is like this. Okay. So now you can see that. Let us show. Say for example, there's a pull on the ring. So from here, yeah. Just a moment. Let me just check it from where it starts. Yeah. One of the nitrogen. So this way. O minus, O minus. Here the lone pair of electrons Oxygen has two lone pairs, but because of this electron which is now been pulled over here, it is getting these three lone pairs. And here, naturally, you have a positive charge. Why positive? Because the electrons which were there are gone to oxygen. Then next would be here. These will, one moment. So you can, these electrons can be shifted over here, the charge can come over here. So you can see this. No, there is no electrons. There is only the charge. And here you are, negative and negative. Of course, there is a charge over here because molecule has to be electrically neutral. Next would be shift of these electrons over here. Again negative, negative. Okay, and here it will be positive. Why? Because these electrons are, the shift is there which is going, so these are different. It's actually towards these, all the three are electronegative element. They are pulling the electron towards itself, and the ring electrons are trying to move over here. And then you can see, now can you tell me where is the positive charge again here in this case, on which positions? Have you understood what?
Ortho and para.
Yeah, very correct. It is at ortho and para position. So now consider it this way. There is no charge on meta position, but there is a charge on the ortho and para position. So
Ma'am, this is
huh,
about resonating effect, right?
yes, this is about resonating effect. Very correct. Fine. Because the resonating effect is pretty big in the book for your syllabus. We were just doing last time what is resonance, what is resonance energy. So far we have done this. Now we are talking about the actual effect, how it stabilizes a given molecule. Okay, the energy is normally less for, that is the resonating energy. The lesser the energy, more stable is the molecule. So now in this case, why is it so less? Because of all these different structures which it gets, which are the canonical forms or resonating structures. That is the reason why this molecule tries to stabilize itself. Now when there, it can be minus R effect or plus R effect. Plus R effect we saw, where we saw that because of the plus R effect, the ortho and para positions, they have high electron density. And now we are seeing that at the, due to the minus R effect, you can see that the electrons are pulled towards the group which is say nitro group or CN group or COH group. But you see that the ortho and para positions have now no electrons, but in fact it is devoid of electrons. The positive charge is there on ortho and para positions. So now can you tell me, compared to ortho position, and understand my this word which I have used, compared to ortho position, can you tell me where is more electron density compared to ortho and para position? Where is more electron density? See, the structure was like this. Huh? माझा प्रश्न कळला का? मी काय म्हटलं की हे असं होतं, O मायनस प्लस O minus, then you had ethane. So here you had plus charge, you had this. Okay. Now next structure would be shift of electrons from this position towards where there is electron, less electrons. Okay, fine. Here you have. Next would be, so now tell me, compared to ortho para position, which have less electron density, where, what about meta position? Do you agree that ortho and para positions there is less electron density or there is a positive charge?
Yes, ma'am.
Okay, when is a positive charge? When there are no electrons. Okay, so now you can see meta position वरती काही charge नाही आहे. म्हणजे at least compared to this, meta position is rich in electrons compared to ortho and para position. कारण आतापर्यंत कुठे charge होता? This positive charge was on the ortho, para again on ortho. But meta position, there was no charge. Even in the earlier case also, but earlier case there was a direct negative charge over here. Whereas here now, meta position is more rich in electrons rather than ortho and para position. Can you, do you agree with me? Have you understood this point?
Yes, ma'am.
Yeah, so that way you can say that now any substitution reaction is going to happen. It will happen at meta position rather than ortho and para position. Whereas in case of the earlier case, there was direct electron density more at ortho and para position. So any substitution which would happen, it would happen at ortho and para positions. Are you getting this?
Yes, ma'am.
शुअर काही डिफिकल्टी नाहीये कारण हे जर नाही कळलं तर अडकल्यासारखं होतं म्हणून मला मी परत परत विचारते सी वी स्टार्टेड फ्रॉम इफ आय रिमेंबर आय हॅव टू गो बॅक अगेन दिस चॅप्टर इज व्हेरी संपला का हा चॅप्टर तुमच्या कॉलेजमध्ये शिकवून
Yes, ma'am. They skipped many topics.
ऑप्शन skip many
They,
yeah okay so now
they,
what happened
ma'am, they only covered the resonance effect. After that, they skipped. And even in IUPAC naming, uh, they are not doing it that briefly as we did.
okay okay fine but you are understanding no my question to you is are you
Yes, ma'am.
following we have done it so you're comfortable with what they taught you over there
Yes, ma'am.
हा त्यांनी तिथे शिकवल्यानंतर तुला कळलं ना
हो, ma'am.
ठीक मग आता कुठचा चॅप्टर त्यांनी सुरू केलाय
आता adsorption आणि I guess fourth chapter.
but what about this other next chapter they haven't as yet started okay fine I can
No.
okay okay fine कधी आहे परीक्षा काही बोललेत का
मॅम आमची क्लास टीचरने सांगितलं की मे ला फायनल्स असणार मेला फायनल्स असणार
Mail a file. Okay, fine. So we have time. That's what these two lectures can help us. Anyways, so we started with this effect. If you remember, why I'm going behind is that electronic effects we are studying. In that we studied inductive effect. If you remember, this was the inductive effect. So you can see that this was that permanent inductive effect, transfer of electrons in that bonded this from towards chlorine. Okay, now this was one effect. Second effect was this was the resonate benzene. First we started with what are the two actual structures of benzene which we normally show. This was it na? The resonating structure of benzene is a hybrid. So these two are the structures of benzene normally we can put in. The properties of benzene can be explained by considering these two structures. The actual resonance hybrid is this structure, and the bond that is single double. These are the bonds which they do not have. They have the same bond length, that is that bond length is in between single and double bond length of carbon. It is not that one bond is single so it is having 1.54 Armstrong unit and the other bond is double so it is having 1.34 Armstrong unit, but all the all the bonds of benzene are uniform and they have the bond length as 1.36 Armstrong unit. So this is about and then there are many other properties, but this was one. So there, and then we came to talk about how do you express any charge. There should be a conjugation. The molecule should be planar. These are also some of the properties which we studied, and then we explain how that different resonating structures can be shown. Now these structures, if you remember, were for straight, that is your aliphatic molecule, but now if you have to show it for an aromatic structure, aromatic structure is nothing but this benzene, then and if you have, then it can have two types of effects, that is plus R effect and minus R effect. So plus R effect is electron donating effect, wherein the group which is attached to benzene ring is ready to give its electron for delocalization, and this gives relatively, I mean this, the electron density at ortho and para position is increased. Then but relatively meta position does not show any electron density increase. But then you have another effect which is called as a negative resonance effect, wherein you can see that the electron density on ortho and para positions is not increased, and hence you can say that the meta position is more compared to the ortho and para position, it is relatively dense, electron dense. म्हणजे तिथे चार्ज काहीच नाहीये, पण जो पॉझिटिव्ह चार्ज ऑर्थो आणि पॅरा पोझिशन वर डेव्हलप होतोय त्याच्या मानाने you can say that meta position has electron density. Now next is your electromeric effect. So is it clear so far? Can I go further now? Shall I go to the next effect, electromeric effect?
Yes, ma'am.
Yeah, this is a temporary electronic effect. Just like inductive effect was a permanent effect, this is a temporary effect, and it is exhibited by multiple bonded groups, particularly carbonyl group. Okay, so in this case, you can see that when a reagent approaches, when any reagent approaches this kind of group, uh, the electron pair gets completely shifted. Now it is a jump of electrons to one of the multiply bonded atoms. So it can be shifted from here to the this. So this is the pi bond system. This is not a sigma bond, it is pi bond. Now you know what is pi bond. We have that they did sp3, sp2 and sp hybridization. So the electrons which are there in the p orbital, they are unhybridized and they can be used to form the pi bond. It is a lateral overlap. So they get shifted to the multiply bonded atom, giving a charge separate structure. So here you are. Say for example, this, of course they have not given much importance to this, not they have not elaborated it for your syllabus. The amount of resonance they have explained here, they haven't put in much. So let us just restrict ourselves to over here. You can see that it is a pi bond effect, and you can see that the electrons over here get shifted towards this. Okay, so this develops a positive charge. If you remember, inductive effect was delta positive charge. Here you can see that there is a full-fledged positive charge which is developed over here. So this is, you can see that positive, and this is negative over here. As long as, sorry, my mistake, it is, yeah, there was this H which we had approached for bonding. So when, yeah, here there is this reagent, acidic reagent, or the reaction is in acid medium, and therefore you can see that this is now a electrophile, that is hydrogen is looking, seeking electrons. So where can it get the electrons from? It can get the electrons from the carbonyl group. Let me put it over here. Say for example, so this is it, that you have put this into an acidic medium. Now what happens is that this carbonyl group, you can see that there is something which is approaching to look out for the electron. Now from where is it going to get? These electrons are already there on oxygen atom. Let me put it, those electrons like this, here and here. Then what happens is that when this proton is approaching, you can see that the electrons are shifted, and you have this kind. So and then these, they can be, so here it is, the molecule will have structure like this. Now, since the electron are shifted from carbon, you can see that it gets a positive charge, and here you have oxygen gets a negative charge. Fine, and then the H is there, which is surrounding. Means it can be used to form a bond over here. But this effect is temporary. The moment this H is out, that is, if you remove the medium which is there, it will go back to its original state. That is, it will come back over here. It is not a permanent effect. It is as long as only the reagent which is going to cause this effect is there. Have you understood? Are you following this? Is it clear? I think Samir, you were not there for some time. Okay. So now this effect is temporary and disappears when the reagent is removed from the reacting system. Now next is you have hyperconjugation. Now this is the last effect in your syllabus for hyperconjugation. It is a permanent electronic effect and explains the stability of the carbocation. So here you have or supposing if there is any carbocation free radical or an alkene. So we have seen this, what are carbocation, what are free radical. So here it is delocalization of the sigma electrons of a carbon hydrogen bond. So here you can see that of an alkyl group directly attached to the carbon atom, which is a part of an unsaturated system or an empty p orbital, or it has a charge. Say for example, this is the group which we are looking at. Now here you can see that this carbon atom has a positive charge. So to stabilize this, the electrons from this carbon hydrogen system, which is attached directly to the carbon having the charge, come into its help, come to help. Now you can also have this kind of a structure, or you can also have this kind of a structure whereas there is a single electron. But what is important is that hyperconjugation is also called as no bond resonance, and this group which is immediately next to the carbon bearing either a free radical or a double bonded structure or a positively charged, there is, you can see that this will be helping it to stabilize. Now, species stabilized by hyperconjugation. How is the stabilization done? So, let us consider this kind of a structure. That is here, this ethyl cation. Here, the positively charged carbon atom, this is the positively charged carbon atom with an empty p orbital has an adjacent methyl group. So, it has this methyl group. So which is an alpha methyl. One of the CH bonds of the alpha methyl group is in alignment with the empty p orbital. The sigma electron of this carbon hydrogen bond are delocalized into the empty p orbital, and thereby they stabilize the cation. So here they have shown with the picture that you can see that this is actually what happens over here is that this is the empty p orbital of carbon hydrogen. Anyways, before that, let me come back to this structure. Acha, I think Samir came. I do not know when he came in between, but Sankalpa, you had lost track. So where were you? Have you understood this other effect? Now I'm talking about hyperconjugation, but have you understood this effect? Because at least you were there. Electromagnetic effect. Were you there during the time when I was talking about this effect?
No, ma'am.
Okay, then let me first explain you this effect. And also Samir if he is there. But then why you people do not tell me that okay you haven't, you just join in but then you tell. See problem काय होतंय की मी शिकवायला लागले मला कळत नाहीये इथे मी हे जातीये म्हणून की तुम्ही बाहेर डिस्कनेक्ट झालाय किंवा नाही. So when you come inside you just let me know that okay I want to know the earlier effect or I want to I'm having some difficulty because I'm just going, what's the point in going ahead if you haven't understood the earlier thing. Of course, no doubt it was not connected, but still I want, since we are going sequentially, I want you to understand this. Okay, so let me know ki, okay fine, I was out for some time, and from this is the point where I was out. So just let me know, tell me, so that I can repeat that again. Anyway, so this effect is a temporary effect, and it is shown by multiple bonded groups which are there, and it is shown in presence of particular reagent. Now in this case, supposing this is a carbonyl group, okay, it is multiply bonded, that is oxygen over here is doubly bonded to carbon atom, okay. And you can see that this is, and we have put H plus ions, means it is the reaction is in the acidic medium. When the reaction is going to be in acidic medium, that time, that is what happens over here is, as the proton is approaching the carbonyl group, the electrons which are over here, yeah, so the electrons which are over here, which electron, these pi electrons, they shift towards on the oxygen atom. Now when do they shift? If you have, say for example, this is in the acidic medium, that H plus is approaching in towards the carbonyl group. So that time what happens is, these electrons are shifted towards oxygen atom. Uh, so then you can see that here the carbon gets a positive charge and the oxygen gets a negative charge, because the electrons are shifted over here, and you have the proton in the system. Proton is seeking electrons. Once they are over here, it can combine with this to form that the this, say, and then you have some other group over here, it can attack over here and the reaction gets completed. But as long as the reaction is acidic, you can see that the electrons, the pi electrons, can be shifted. Similarly, this effect can be seen very well on such CH2. Say for example, you have over here cyano group. No, any group which is there, these electrons, this effect can be transferred from one carbon to the other carbon atom. So you can shift this over here and you can show it this way. These, the electrons, the pi electrons between, now say supposing 1, 2, 3 and 4, can be shifted towards, between now 1 and 2, they have shifted between 2 and 3, and the one which was on between 3 and 4 has been shifted towards on the fourth carbon atom. Okay, so this way the effect can be shifted and then naturally this gets a positive charge. So how many conjugated double bonds over there, you can shift this straight away along the, it is not a partial charge, the effect is felt equally over the whole of the molecule. Same thing over here, this was just now that example what we took, this was in presence under acidic conditions. What happens over there is that you can shift the pi electrons on the electronegative element. Supposing if over here you have cyano group also, you can attach over here. Yeah, but here they have shown, they haven't taken this kind of an example. I had taken this example. So this you can see that over here, in presence of acidic medium, you can see that this is shifted on the oxygen atom and this gets the positive charge. Same over here, you can see that. So one moment. This electromagnetic effect is also called as polarizability effect. That is, you are introducing some polar this, and this kind of an effect is present whenever there is a reagent present. When there is no reagent over here, say for example, if there is any reagent or which is ready for the reaction, that time only this effect is seen. Otherwise, this effect is not seen. Okay, here also you can have minus E effect. This is called as electromagnetic effect. So it can be minus E effect and plus E effect. That is, groups which are going to pull the electron towards them is they are minus E effect, and the groups which are going to uh, uh, give the, I mean, the effect which is seen wherein it can be also a plus E effect. So these are, that is inductive effect, resonance effect, and electromagnetic effect. I just tried to show you that this effect can be transferred over a whole ring. Say for example, again you have this type of, I mean, I'm showing the conjugation which is still longer than what I showed you just now. CH2C double. Okay, now this kind of a molecule is there. Then in presence of any reagent which is going to pull the electrons, you can show this effect over the whole molecule till it comes on this carbon atom. Okay, and this carbon atom. So when these electrons are shifted from here, you can see that this is positive. This is, the double bond is shifted. That is, the pi electrons are shifted. Supposing if I number it as 1, 2, 3, 4, 5, 6, 7, and 8. Now here you can see 1, 2, 3, 4, 5, CH. The negative charge comes over here. 4, 5, 6, 7, and 8. So this is the shift of pi length. So here you can see that this carbon gets a positive charge, first carbon atom, and the last carbon atom gets a negative charge. So this happens in case of reagents. In your book, they have not taken this effect, this example, but I just wanted to show you the shift can happen. In case you come across something like this, they have just taken a simple example over here. Okay, so now is it clear this effect? So this is opposite to inductive effect. Inductive effect, what we talked about was, it was a permanent effect. That is, it was the inherent property of that molecule. Say for example, CH3, CH2, and Cl. Then you have this as partial positive and partial negative, delta negative and delta positive. Here it was delta delta positive. But if you have this effect just now which we discussed about, that is CH2 double bond CH, I'm just comparing these two effects. This is inductive, this is your polarizability effect, yeah, electromagnetic effect. Sorry, electromagnetic effect. In this case, in presence of a reagent, supposing you have this molecule, I will show it like this with a smaller one also. So here you can see that let me take a double bond and then you have CH2. So these electrons are shifted this way. Okay, now here there is a delta charge. Here there is, you have a full-fledged positive and negative charge developed. So here you can see that this becomes positive, this double bond, and then you have CH2 minus. So you have positive and negative charge. Here you have delta positive and delta negative charge. This is a shift of sigma electron. These are sigma. There is no pi bond over here. Here these are the shift of pi electrons. Okay, so this was about the inductive and electromagnetic effect. Resonance effect also we did just now. Now the last part is hyperconjugation. Now hyperconjugation is something like, let us first look at the, just 5-10 minutes I'll continue. Yeah. So here you are, in case of hyperconjugation, it is the delocalization of sigma electrons. Between which sigma electron? These are the sigma electron which are going to help this carbon atom. So any group which has got, say for example, if there is, this is carbocation, and if you have CH3, okay, similarly I'm not putting all the CH3. This is a tertiary butyl carbocation. Okay, so these are the sigma electrons over here. These are the sigma electrons which are this. There is a empty p orbital over here. So these sigma electrons, they can be delocalized over this p orbitals, or rather, how they help over here is that you can see, one moment. Let us look at this. I'm going directly to the next page. So see, you can see over here is that hyperconjugation is sigma pi conjugation. That is, these electrons over here have come into stabilize this positively charged carbon atom. So there is this positively charged carbon atom is having a empty p orbital, and these sigma electrons of this hydrogen can be delocalized over here. So here you can see that the more the number of such structure, the better is the stability of this carbocation. Such as hyperconjugation is called as no bond resonance. So always you can see that this, say for example, let me just show you over here. This is the positively charged carbocation which is not stable. Let me put over here as other two as hydrogen, but this carbon is having, it is a methyl group. So now this hydrogen, it cannot be utilized, but the sigma electrons of this hydrogen can be used. How can they can be used? They can be used over here, that is, they get shifted over here. So you can see that now the valency of this carbon becomes 4, and the charge now will be shifted for a temporary this towards over here. Okay, so you can see that now this hydrogen has given its electron. Similarly, this hydrogen can give its electron, this hydrogen can give, and this molecule becomes stable till there is some other group which is going to complete this reaction. So the more the number, but these hydrogens cannot give there because they see the carbon valency, they can't break and then give it because they are directly attached to this carbon atom. The sigma electrons which are on the alpha carbon atom, this is the alpha carbon atom, and the electrons of the alpha hydrogen atom, they help into this resonating structure, and it is called as no bond resonance. It is also called as hyperconjugation. This is called as hyperconjugation. Okay, let me explain you this next time, next lecture. Next lecture we will be starting with this part, and then I think that's the end of this chapter. Only this much is there, and then after that the exercise is there. What I would like to tell you is try to solve these exercise questions and then ask me, because even if they haven't done in your class, college, they will be helpful to you in your 12th standard. Whatever you don't understand or you don't follow, we can rework on it, that this part I haven't followed. But right now, I hope you have followed. These are the different effects which we were looking into. And out of that, hyperconjugation, I think, could be little more tough to understand. We can do it next, that is today's Wednesday. On Friday, we'll be meeting again. So let us stop here. I hope few things which we on, if you think that they are not clear, let me know by Friday. We can complete that. Is it okay?
Okay, ma'am.
Fine, good. This is the last part, and then we can start with the other chapter, which is relatively smaller, that can be completed. And then I think alkanes is there. Alkanes, alkyne. That is very big. Anyways, thank you so much. Yeah.
Thank you, ma'am.